Hi, and welcome to 5.3 Kinetic Friction and Accelerating. In this video, we look at situations where there is a net force acting on the object, causing it to accelerate. However, there's also friction that we have to take into account. So it's kind of a culmination of the past couple assignments we've been doing. We start with some multiple choice. Number one, as more force is applied to a steel box sliding on a steel surface, the coefficient of kinetic friction will decrease, increase, or remain the same. Remember, the coefficient of kinetic friction is just a ratio of the frictional force to the normal force. If you increase your applied force, it's not going to change either one of these variables. Another way to think of the coefficient of friction, it's just a measure of the roughness between two surfaces. So yeah, you could push as hard as you want. It's not going to change the steel box into a different type of material. It's not going to change the steel surface into a different type of material. So the coefficient of friction stays the same. All right, they're specifically asking for the coefficient there. Okay, number two. The table below lists the coefficient of kinetic friction for 4 materials sliding over steel. A 10-kilogram block of each of these materials is pulled horizontally across a steel floor at constant velocity. That's important, the fact that they're telling you it's constant velocity. Which block requires the largest applied force to keep it moving at, again, they say it again, constant velocity. Here's why that's important. If you have a block and you're applying a force, and there's a frictional force opposing your motion, that's the situation. You also have Fg and the normal force. All right. But here's the situation. You're moving at constant velocity. So that means you have no acceleration. If you're not accelerating, Newton's second law says that the net force is directly proportional to the acceleration. If this is 0, that means the net force is also 0 newtons. So that means that the forces are balanced. They're canceling each other out to get a total force of 0 newtons. Namely, the applied force is exactly equal to and opposite in direction to the frictional force. So when they're asking which block requires the largest applied force to keep it moving at constant velocity, they're really asking which one has the greatest frictional force. Right? Because if this is the largest applied force to keep it moving at a constant velocity, which situation will give you the greatest frictional force? So in essence, they're really asking which one has the greatest frictional force. And they tell you all the different coefficients. Now, what else do we know? The frictional force is equal to mu Fn. Now, what are they changing? They're changing the coefficient of friction. They're changing mu. So as the coefficient increases, the frictional force will also increase. It's a direct relationship. Is there anything, do we have to worry about the normal force here? Let's see. It says a 10-kilogram block of each of the materials, and it's a horizontal floor. So Fg is also always going to be equal to the normal force. At least their magnitudes are equal to each other. They're opposite in direction. So technically it'd be like this. All right. In essence, the normal force isn't changing here. We're only caring about the coefficient. So we want the largest coefficient of friction. That will give us the greatest frictional force, which will cause us to have to pull with the largest force to keep it moving at a constant velocity. So as you can see, steel on this surface will create the greatest frictional force. Steel. Okay, number 3. A 75-kilogram copper block is being pushed across a steel surface by a force of 300 newtons. The block's initial velocity is 5 meters per second, and it's pulled until it reaches a velocity of 20 meters per second. Interesting. So the velocity is increasing. That means it's accelerating. That means there's a net force acting on the block. That means the forces aren't balanced like they were in the previous problem. It's not at constant velocity. So it says, draw a free body diagram of the block. Okay, so we have our block. Fg is always a good place to start. It's on a horizontal tabletop. The normal force is equal to Fg. You're being pushed across a steel surface by a force of 300 newtons. It doesn't say what direction that force is acting, so I might as well just make it pushing it to the right. It's kind of my go-to direction. And we also have friction. Now, I'm going to draw this friction smaller than the applied force. How do I know it's smaller than the applied force? Like we said, there should be a net force acting in the same direction as the velocity. So the applied force is greater than the frictional force because when you add the two together, you get a net force, which causes an acceleration. Then it's a scaffolded question. So then it says, what is the weight of the block? So you do Fg is equal to mg. Fg is equal to 75 times 9.8. I skipped a step here. I should probably just write my givens in, just so I don't get points off for units. Meters per second squared. You could even do VI is equal to 5 meters per second. VF is equal to 20 meters per second. And that's all we know from a kinematic standpoint. We don't know the acceleration, we don't know the time, and we don't know the distance that it travels. All right, but we can figure out Fg. Fg is equal to 735 newtons in the negative direction because the gravitational field strength is in the negative direction. So this is 735 newtons down. We use the arrow to show the down direction in the free body diagram. Then it says, what is the normal force acting on the block? That's just 735. All right. How do we know that? The forces are balanced in the y direction. It's not accelerating anywhere, so they're equal to each other in opposite direction. What is the frictional force acting on the block? Okay, so Ff is equal to mu Fn. We just figured out what Fn is. We should be able to figure out what the coefficient is. Let's see. It's copper on steel. So let's look in our handy reference table. Copper on steel, up on the back page here. Let's see. Copper on steel. Right here. Is it kinetic or is it static? Well, you have an initial velocity and it's just getting faster. You're moving. Anytime you're moving, you're sliding, it's kinetic. So we want to use 0.36. 0.36. Times the normal force, 735. So the frictional force is equal to, let's call it 265 newtons. Now, it's important to note, like, we got a positive number for this, but we were really only calculating the magnitude of the frictional force. Since we drew it going to the right, like the velocity is going to the right, the frictional force is going to the left, you could think of this as a negative frictional force. It's just showing the direction. In our case, it's going to the left. That's going to be important for letter E. It says, what is the net force acting on the block? Hint, use your free body diagram. To find the net force, sometimes people are tempted to do MA, right? So that's a totally valid equation, but we don't know what the acceleration is. So we can't really use that form. So we have to go back to the definition of the net force. The net force is equal to the sum of all the forces. That's what this weird symbol is supposed to be. It's a hastily drawn sigma, which stands for sum. You might know from your math classes. So the net force acting on the block. Let's only look in the x direction. So we have the force of friction, and we have the applied force. We're not looking in the y direction. We know those two cancel out anyway, so we'll just look in the x direction. So you write in the force of friction plus the applied force. Just like that. It's the sum of the forces. Don't get ahead of yourself and start making things negative. No. You make them negative when you plug them in. That way you don't confuse yourself. It's just the sum of all the forces, and now you ask yourself, okay, what direction is the frictional force going? I drew it going to the left, so you make that negative. Plus the applied force. That's going to the right. 300 newtons to the right. So the net force is equal to the sum of those two forces, which is 35 newtons to the right. You get a positive number, which makes sense. That's what we would expect because you're accelerating to the right. You're getting faster in the direction of your applied force. So then it says, what is the acceleration of the block? It even tells you use Newton's second law. So now we could use that net force equals ma equation, or since we're solving for the acceleration, we might as well use the version of Newton's second law that is already solved for acceleration. So this is 35 newtons to the right, and the mass, they tell us, is 75 kilograms. So the acceleration is equal to 0.46, repeating, we could call it 0.5 meters per second squared. That's fine. To the right, you get a positive number for a reason. Then it says, for how many seconds is the block accelerating? Think kinematic equations. Hint, kinematic equations. So here was our kinematics data, the velocity. Now we know the acceleration is also 0.5 meters per second squared. They're asking for the time. So we don't care about the displacement. We want an equation without displacement. So you could do VF equals VI plus AT, or the definition for acceleration, the change in velocity divided by time. I prefer the former. Former, right? Yeah, former. So VF is equal to 20. VI is equal to 5. This is 0.5. And you're looking for T. So you get 15 is equal to 0.5 T. The time is equal to 30 seconds. Very good. Okay, that was pretty good for number 3. Number 4 is a curveball. You definitely want to try number 4 on your own first, because I'll show it to you and you'll probably and hopefully you'll understand it. That's not the purpose of asking a question like this. On your final exam, on your Regents exam, they're going to try to throw curveballs at you that you'll have to use some critical thinking. You'll have to look at the information that they give you and figure out a different way to solve for the problem. We've been doing problems where it's just like, okay, if they're asking for the friction, let me use the friction formula. In this one, you have to do it differently. So definitely, that was a hint. Definitely try to figure out, okay, what do they give me? What do I want to try to figure out? How can I do that using a different equation? So try it on your own first and then watch the video. It says the diagram to the right shows a 2 kilogram object accelerating at 5 meters per second squared on a rough horizontal surface. What is the frictional force acting on the object? Again, you might want to try to do this guy. And you're in luck. You can figure out what the normal force is. But when it comes to the coefficient of friction, they just say it's a rough surface. They don't tell you what the surface is. They don't tell you what the block is. So you can't use that formula. We're going to have to figure it out in a different way. Let's write down what they give us and see if any of that stuff helps us. Just start writing it down and see if you can figure out a different way to do it. So the mass is 2 kilograms. The acceleration is 5 meters per second squared. And the applied force is 50 newtons. That's all they got. Look at what they give you. Improvise, adapt, overcome. Knowing the mass and the acceleration, what could you find? Possibly the net force. Net force is equal to ma. Not sure why we're doing this yet, but it looks like this might be useful. Now we know the net force is 10 newtons. So that means when you add the applied force and the frictional force together, you should get 10. Interesting. You might be able to figure out what the frictional force is at this point. If you wanted to write another equation to try to help you, it might look like this. So here's the first step. The second step is, again, we're starting by looking at the net force. But now the definition of the net force is that it's the sum of all the forces. So the frictional force plus the applied force. Now let's plug in what we know. We figured out that the net force is 10 newtons. We're looking for the frictional force. That's okay. That's what they ask you. I hope we know what the applied force is. And yes, we do. They told us it's 50 newtons. Now all you have to do is solve for the force of friction. You subtract 50 from both sides. The frictional force is actually equal to negative 40 newtons. You did not need to know the coefficient. We've done problems like this before, actually, with the Newton's second law. It's just that instead of calling this F1 and F2, we called it the frictional force and the applied force. So you've seen problems like this before. It's just framed in a different way to make you think you have to use the frictional force equation. You have to be able to think on your feet in physics and in life. So this is a good lesson. Now it says, what is the coefficient of friction between the object and the surface? Okay, they're asking for the coefficient. They don't tell you what the materials are. We're probably going to have to use this formula. And we know what the frictional force is. It's 40 newtons. Again, I could just use the magnitude of the forces for this problem. And we don't know what the coefficient is, but that's okay. That's what they're asking for. But what is the normal force? We should be able to figure out what the normal force is. We know Fg, in this case, the force due to gravity is equal to the normal force. So all you have to figure out first is Fg is equal to mg, just like those other problems we've been doing. The mass is 2 kilograms. This is negative 9.8 meters per second squared. Don't get points off for units. So this is negative 19.6 newtons. So that means the normal force is 19.6 newtons. And you could plug that in right here. The coefficient should be around 2. Yeah, that's about 2.04. All right, again, no units for the coefficient. Just quickly before we leave, let's talk about that. You might have noticed that's kind of a big coefficient compared to the ones in your reference table. It is possible to have a coefficient that's greater than 1 and even close to 2. Coefficients greater than 2, I would say, are pretty rare, but they can happen because remember, the coefficient of friction is just the ratio of frictional force to normal force. So if that ratio happens to work out like that, that just means you have a very rough surface. All right, have a good day.